Morning. So before I begin, I want to ask quickly about project. Submission is tonight. There won't be any extensions. I just want to make sure where we are all at. Can you just like one representative per group can speak?
We're done. Like,
Did you upload already?
we just have to upload it.
Okay.
Pretty much.
Good.
We're submitting.
Submitted? Good.
We're finished to upload.
Have to upload? Okay. So, converting the video file to Excel or Excel? Okay. Okay, plotting. Okay.
We just have to do scaling analysis. And then the extra part, which is like, I guess, find the discovery. We where that was, I just have to do more research on that.
Okay, but you're sure you can submit by midnight?
We have all the videos, and we did the, all the Excel besides the discovery analysis.
Okay, only scaling analysis. Same group? Okay. Brian? Okay. How's your group doing? Will you be able to submit by tonight or midnight?
Yeah, we did like 90% of it yesterday. We got the videos and the Excel document. We just don't have scaling analysis. And I
Okay,
have to filing like a voiceover for the videos.
good. So you're sure by midnight you'll have it? Anybody else that's not part of these groups? Okay. Okay, good. So other than that, I also want to ask, have you had a chance to look at the recording for module 7 that I posted? At least spend 20-30 minutes per day. I asked you to do that. Have you watched some portions at least, if not all? How many parts have you watched? Like,
I watched all.
awesome. I like it. Okay. Anybody else has watched at least the first 3 or 4 parts? How many did you watch?
I'm halfway through part 4 right now.
Okay, I mean, nothing is more than 20 minutes. Some of them are only like 3-4 minutes, so you should be able to quickly.
I fell asleep, so I had to.
Was it so boring?
No, I was just tired that day. It was yesterday.
Okay, so you should have said that first. People will think it's very good. Okay, anybody else has started watching the videos on module 7? Since nobody wants to make eye contact, I assume that's a no. Okay. Okay, please don't ignore that because the recordings go into pretty good explanation about the concepts in module 7. Brian, you watched it all the way, right? Did you think it was helpful? It helped you learn the material?
That's pretty well done.
Okay, I just have to back it with examples here. Okay, so we'll do that. Okay, so towards the end of last lecture, we saw the definition for Reynolds number. Reynolds number is rho B D over mu. Rho and mu are fluid properties, density and viscosity. Okay, and V is a characteristic velocity in that flow. Characteristic velocity in that flow. And D may be diameter, but it's also typically a characteristic dimension. It could be the diameter for a circular tube, characteristic dimension. Okay, examples for a pipe or a tube that is circular. If it is circular, the obvious dimension to use would be diameter. What would we do if it were non-circular, something that doesn't have an obvious principal diameter? Okay, so when you think of a pipe, you typically think of circular cross section. Okay, and for which if there is a diameter, that's the dimension we would use to calculate Reynolds number. If it were a non-circular pipe, like you can have a pipe that looks like a triangle or a square pipe. So what we do is we define what is called as DH, hydraulic diameter or hydraulic diameter. Let's say we give the symbol DH. DH is 4 times the cross section area divided by the perimeter of the shape. So for a square DH would be 4 times the cross section area, which is side squared, divided by the perimeter, which is 4 times the side, giving us the side for a square. Okay, and for a, let's say, a triangle with 3 equal sides, for example, hydraulic diameter would be 4 times the area of a equilateral triangle. Let's say the side is A. So that would be half times, what is this side? This is A over 2 times root 3 over 2 times A, divided by the perimeter, which is 3. Okay, so that would be A divided by square root of 6. Oh, sorry, square root of. So this is just a adjustment we make for non-circular pipes, but most of the discussion that we are going to have is done around circular pipes, but can be easily extended to non-circular cross section. Still something that we need to understand. And then we talked about developing length for a pipe flow. Anybody recall what is developing length as we discussed it last time? Yeah,
I don't know.
say it in simple words, doesn't have to be super precise.
It goes from like an even flow to a disturbed flow, I guess. I don't know.
So you have a pipe, okay, let's say the flow enters here, when it enters the pipe, it has uniform velocity. So it has uniform velocity profile when entering the pipe. Okay, and what happens as soon as it enters, what happens between the fluid and the wall? Friction. Friction at the wall starts acting on the flow, slowing it down. So what happens is a part of the flow that is nearer to the wall slows down, whereas the flow that is still far away from the wall continues like as though it is still inviscid. So this portion is inviscid, whereas this portion becomes viscous. So we have the penetration of the effect of the wall throughout the cross section. Slowly, it starts at the wall, a smaller region becomes decelerated or becomes viscous, and then a larger region remains inviscid. And as the flow goes downstream, this portion gets more and more larger, that is, the viscous portion gets larger, whereas the inviscid portion shrinks in the cross section. And at some point, the flow becomes fully viscous and it attains what is classically called the parabolic flow profile, which we are going to derive today. Like we are going to go through a derivation and reach that mathematically. So then here it becomes fully viscous, or we call it fully developed. This length from the entrance to the point where it becomes fully developed, this length is called entrance length. It's a term that is commonly used in pipe flow or fluid thermal design. So you have to remember the definition. People will say for a given Reynolds number, estimate the entrance length, because the entrance length is a region where the flow is changing in an unsteady manner. After it becomes fully developed, it becomes steady and kind of makes it easier to analyze after that. So this portion here is a region of unsteady flow and velocity and changing velocity profiles. Whereas once it becomes fully developed, the flow becomes steady as long as the upstream cause that is causing it remains steady. The flow is steady to the extent that the upstream is steady, and analysis is simpler because the velocity profile does not change with length downstream. That is, after this section where it becomes fully developed, if you observe the velocity profile, it will remain the same further downstream. So let me ask a question here. Let's say in this reservoir, the reservoir is simply like a tank. It contains the fluid at a higher pressure. It could be a tank that is attached to a compressor where the air is stored, let's say at 60 psi G. You know that 60 psi G essentially means 60 psi plus whatever G means the gauge pressure, which is like 14.3 psi, which corresponds to atmospheric pressure. So let's say you have a tank that contains pressurized air. My simple question for you is, as you connect a tube or a pipe to the tank and let the fluid discharge through the pipe, what happens to pressure if you measure it at every cross section? Will pressure remain constant or will the pressure keep dropping? Keep dropping. Why?
Because the energy gets taken by the.
Friction. So what is pressure? Go back to the beginning of this class. What did we think pressure is? It's a manifestation of. Pressure is a manifestation of the thermal motion. You have a high pressure, meaning you have compressed the gas or liquid to a higher pressure where the molecules are all jostling around. As the fluid goes through the pipe, viscosity or fluid friction at the wall essentially converts that energy into heat, and that heat is basically removed through the walls of the pipe. So what you feel as a pressure drop is essentially a conversion of energy from thermal motion to heat, and that heat escapes the pipe through the walls. So then the question is, if I ask you to, can I erase these words? Yes. So if I ask you to plot as a function of distance along the pipe, distance along the pipe, and here is your start or entrance. Here is my starting pressure, so I'll call this P reservoir, which is the pressure at which you are starting the flow. You told me already, as we go to the further along the pipe, the pressure is going to drop. The important question is at what rate? That is, will it drop like this, drop like a stone, or will it drop at a linear pace, or will it drop at a very, very slow pace that it's almost imperceivable, like it's very hard to perceive? At what rate will it drop? That's the question we want to think about. Okay? It's not easy to analyze this region, at least within the tools that we have learned in this course. Analyzing and predicting at what rate the pressure will drop between the start and the point where it becomes fully developed is not easy to analyze. What is easy to analyze though is After it becomes fully developed, the pressure starts dropping linearly. That is, the fully developed flow is characterized by linear drop in pressure with distance along the pipe. What I'm trying to say is, if you just for 1 minute take a pause from writing, I'll give you a gap to write. Okay, this I want to make an important point. For 1 minute, just forget the developing portion and focus on the developed portion. Okay, in the developed portion, when I say the analysis is simpler, what I mean is, if you take a length of piping, let's say we call this length L, and over this length L, let's say the pressure drop is delta P. And if I tell you the pressure drops linearly with distance, for a pipe length of 2L distance, what do you think the pressure drop would be? If it drops linearly, for a length of L can be like 10 centimeters or 2 meters or anything. For a distance L, if the pressure drop is such some number, what will be the pressure drop for twice the length of piping?
Like half its original value.
Sorry,
It'll drop to half its original value.
it will be twice as much, right? That is, if you are just dropping at a linear pace, if you double the length, you should double the pressure drop. What were you saying?
The way you said.
It should be 2 times delta P. Okay, so when it comes to fluid analysis, the bigger role of entrance length is to first determine whether the entrance length is a significant or an insignificant portion of the total length. So think about it like this. Think about it like this. Let's say this is the total length of pipe that you need to analyze, okay, or that you need to understand. Okay. The entrance length, let's say we call this portion LE, the entrance length. Okay. Usually LE over L is a small number, meaning the entrance length is only a very small fraction of the total length. Okay. In the developed portion, delta P scales linearly with length. How do I know that? Well, we'll do a derivation that will kind of put that in place mathematically. I'm just doing this discussion ahead of the derivation. Why? Because there is a very important practical reason why we should understand the entrance length relative to the total length. So you need a method to calculate entrance length. Okay. So how to estimate entrance length? So for that, you want to refer to equation 8.1 and 8.2. Okay. For laminar flow, entrance length is 0.06 times the Reynolds number multiplied by the diameter of the pipe. For turbulent flow, LE is 4.4 times Reynolds number to the 1/6 times D. So this is, if you see the mock exam, I have a problem on there that asks you to calculate the entrance length for a flow with a certain Reynolds number. Okay, so usually fluid mechanic analysis or pipe flow analysis starts with the first step, estimate Reynolds number. Second step, determine if whether the flow is laminar or turbulent. And third step, estimate the entrance length. This is required to establish that LE is a small fraction of the total length and use simpler analysis. Simpler analysis for fully developed flow, which we'll see now. Okay, that is the next step. So an important skill for you when you do your pipe flow analysis, you're designing or calculating the pressure drop or the flow rate, is first to understand based on nominal values, what is the Reynolds number. So how do you estimate Reynolds number? We need some practice on that. How to get Reynolds number? Reynolds number is rho V D over mu. Okay. Rho V D over mu, where I told you rho and mu are fluid properties. Fluid properties. And V is typically the flow rate divided by the cross section. And D, in our case, will almost always be the pipe diameter. Okay, let's do a couple of examples. Okay. Problem 8.5 from the text. To cool a given room, it is necessary to supply 4 cubic feet per second of air. So I'll give you that 30 seconds now to catch up on the writing if you want to.
So, we determined that it's not, we can't tell like I guess the curve of pressure from entrance to.
And this is okay, you're talking what happens here. Okay, so this is linear. Okay. There is this portion, what happens here? That is your question, right? Doing it through calculations is usually very difficult. What we typically do is, if suppose you have a situation in which the entrance length is not a small portion, but a significant fraction, let's say 30% of your pipe length is entrance length, what we do is, we have to plant pressure transducers at various locations so that you can actually experimentally measure it and understand at what rate it is dropping. So whenever you can't theorize or calculate, you measure. Okay, because measurement will be something that directly gives you the truth instead of you having to theorize or approximate. So when people did that, again, these are all stuff that was done nearly for the last 200 years, since like 1800s. Okay, so what we do know is, in this portion, the pressure falls faster than linear. That is, once that is in this portion, pressure drops faster than length, or it could be L to the alpha, where alpha is greater than 1. It typically falls faster than linear. It could be quadratic or between 1 and 2, let's say. But once you hit the fully developed flow, it becomes linear and the analysis becomes simple. Yes.
Alpha like usually a very, very, very small number.
It's a number that's slightly larger than. It falls faster than linear. That's what I mean.
Okay.
Okay. I mean, if it falls as to the power L exactly, it means it's linear. I'm saying it falls faster. So if you double the length, instead of getting double the pressure drop, you may get 2.2 times the pressure drop. That's what I mean, falling faster than linear. Okay, faster than linear. So throughout undergrad fluid mechanics, even in industrial practice, our impulse is always to determine what is the entrance length and show that it is like a very small fraction of the total length. Suppose you are laying pipe that carries water or gasoline or something, and the pipe length is, let's say, 200 meters, and your entrance length turns out to be half a meter. You make the case that entrance length is a very small fraction. So we neglect what goes on here because in the bigger scheme, including that won't make a difference. It's not worth the trouble of doing more analysis. So you say that analysis may be neglected, and we'll stick to the easier analysis because it's easy and it's quick and it's pretty accurate. Okay. So that's why knowing how to estimate the entrance length matters, because you have to then use it to say it's not important. You can't say something it's not important if you can't know how much it is. Okay. I'll keep this. Can I erase the other side? Yeah. Okay. Okay, we want to do problem 8.5, where we are told air at a rate of 4 cubic feet per second is used to cool down a room through an 8-inch diameter pipe. Okay, approximately how long is the entrance length of the pipe? So you're asked to calculate entrance length. And this problem is very similar to the problem I had in the mock exam. Okay, so the steps. Okay, first step, identify the fluid. The fluid, which is in this case air. So if it is air, standard air, you can say the density is around 1.2 kilograms per meter cube, or you can use the tables. And viscosity is around 1.8 times 10 to the minus 5 Pascal second. I'm writing this down because I know this number. If you don't know, you would refer to the tables, property tables. Look up for standard temperature and pressure. Okay, the diameter is given as 8 inches. I don't have a very strong command of English units, so I like switching to SI as soon as I get the numbers. So that's 8 inches times 0.025 meters per inch. So that's how many? That's 0.4 meters. Okay. And Q is 4 cubic feet per second. I do know that 1 foot is 30 centimeters approximately. So this is 120 cubic meters per second. And 1 centimeter is 10 power minus 2 meters. So this is 120 times 10 power minus 6 meter cube per second, or 0.12 times 10 power minus 3 meter cube per second. See, this is what I mean. I want you to observe. You know this conversion. you know these conversions and you should be able to quickly think on your feet and get into a consistent system of units. If you are comfortable with English units, you don't have to do this. I'm not, that's why I'm doing it. So always the progression is to get entrance length, you need Reynolds number, and Reynolds number is rho Vt over mu, which means you still need velocity, which is the average velocity q over a. So this would be 0.12 times 10 power minus 3 meter cube per second divided by pi by 4 d squared, which is 0.4 squared meter squared. Can you punch this number and tell me, because I got a request last time that we should follow through with the numbers. They don't like to do, but still do it. Can you please punch this and tell me? We should get some meter per second.
I get 9.4.
9 point?
I get
0.55, 10 to the negative 4.
yeah.
Come again?
9.55, 10 to the negative 4.
Okay. 9.55 times 10 to the minus 4 meter per second. Okay. So you get a number like 9.55 times 10 to the minus 4. How do you kind of quickly judge whether that number makes sense or not? If you had seen this flow, what this statement essentially says is, this is about 9.55 times 10 power minus 1 millimeter per second, or about 0.955 millimeter per second. This is like saying 1 millimeter per second. So it's like saying the flow, the air through the pipe is advancing at the rate of 1 millimeter every second. So this to build intuition, we can't just rely on just the numbers. You have to actually see the flow, like observe something with your own eyes and see if this number actually correlates with what the flow does. That is why in your funnel experiment, you are asked to see the flow and get the velocity from that. You have done the measurement, right? You tell me with what velocity is the soap solution dropping out of your funnel. You would have seen the numbers. Any numbers you want to throw around in your experiment? You have the numbers, just tell me what you remember.
But will like
In your experiment, what velocity did you measure for the velocity for the soap? Louder?
0.435.
In what unit?
Meters per second.
So that's like 430, around 435 millimeter per second. Sounds like a lot. Fine. Any other numbers? Okay, let's not spend too much time here. Come back here and now compute the Reynolds number. 9.55 times 10 power minus 4 meter per second.
25.5.
25.5. That's the Reynolds number you're getting. We'll call it 26. Okay, now comes the important question. Reynolds number is 26. Should we consider that to be laminar flow? Should we consider that to be turbulent flow? This is an important question in fluid mechanics. Based on the flow conditions, how do you predict whether it's laminar or turbulent? Okay, this will happen again and again in any fluid mechanic problem, whether it's internal flow, pipe flow, or external flow, or flow over bodies. Before that, we technically haven't talked about what is laminar, what is turbulent. Okay, so let's go there, talk about laminar versus turbulent, and then we will look at a condition that will help us decide Reynolds number. Using the Reynolds number, we can decide whether it's laminar or turbulent for a pipe flow. Okay, we'll keep this and come back to this at the end of the discussion. So drop your pencils for a second. What do we understand by the term laminar flow? What do we understand by the term turbulent flow? Can we start there?
Laminar means that the flow is completely uniform,
Uniform with respect to what?
diameter.
I don't understand what that statement means. Uniform with respect to diameter as well.
So most laminar flow is like.
If you want to define something like laminar flow, you have to define it without using the word laminar.
If you,
An attribute of the flow, how to use that attribute to define what is laminar.
Using it as like a correlator, not as like a definition.
I need a definition. So hold your thought, I'll come back. You wanted to say something?
Is it just like where the flow doesn't vary locally?
The flow could vary locally, that could still be a laminar flow, so that's not it. But I know what you're thinking. Can you think again and try?
if you graph it with the velocity with respect to time,
Forget graphing. I'll pick a sixth grade student for you. Explain laminar flow to that student. What words would you use? No graphing, no fancy words.
the velocity at a certain point is always constant.
Sorry?
The velocity at a certain point is always constant.
That will make it a steady flow, not a laminar flow.
Smooth.
Smooth respect to what? Again, I don't want to pry words from your mouth. If you want, speak in complete sentence. I'm not going to expand your words.
Well, I mean, if I was good at explaining to a sixth grader, the word I would use is a smooth flow.
As they might think it's some kind of egg surface which is smooth. So when you say smooth, what is smooth here? Anybody else wants to talk?
Not a lot of random fluctuations.
Like laminal,
Come again?
laminar flow,
Yeah, but I'm asking you to define what is laminar.
non-turbulent, non-disturbing.
Okay, we are not playing that game. Yes. You want to talk about fluctuations?
It doesn't have like a lot of fluctuations or like random and abrupt fluctuations.
Okay, so you're trying to define laminar in terms of what it is not and what not what it is, right? That's okay. That's what you're trying to do. So we need a way to think about what is laminar. First of all, think of the word. What does laminate mean? What does laminate mean? When you laminate a picture, what are you doing?
To enclose or
To have a sheet cover a surface. That's what laminate means, right? Right? Is my understanding of English correct? I'm not a native speaker. Laminate means in sheet, have a sheet. Laminar is essentially, if I think of a pipe flow, by laminar, what I mean is the fluid after it enters and after when it's flowing through, it's flowing in sheets or layers which don't mix with each other. That is, if you think of it as rivers, if you get on this river here, the river is so steady, it is moving in sheets that your destination is definitely over here, and there is no way you can make it to another river or another river or another river. That is, the flow is so steady, it has to be steady. You can't have unsteady, or you can't have a laminar flow that is too chaotic. Laminar flow has to be steady to an extent. It is steady and takes place along certain planes or layers or laminate, so that the fluid molecules have a very deterministic path and they reach a certain point. This is what laminar is. It is flow that takes place in layers that don't mix significantly or appreciably. That is, if you drop in your cone and soap experiment that you did, if you drop some dye at a certain location, you can almost see the dye coming out at the same location on the exit. It won't come at any other point because the flow happens to be laminar in that case. So what is now the hallmark or a characteristic signature of laminar flow? If somebody asks you, if I want to detect a laminar flow, or if I want to look at a flow and see whether this thing is laminar or not, what would you use as a marker or a test?
The
The
rental
direction.
Sorry, we are in the middle of something. I don't, that's not the question.
The direction of the flow. If it's
So how you would think about it is, think of a river. Okay, suppose there is a flow that's progressing this way, and I have three tiles here. Okay, I'm here on the leftmost tile. If I drop some dye here, and the flow doesn't mix it across layers, the flow happens in uniform layers. That the dye that is injected here travels almost in a straight line or follows the flow such that it can be found only in that layer and not in another layer. So to kind of think about it, here's an example. Let's say we take the map of the US, okay, kind of an approximate map. That's this Texas, maybe some more Mexico. So there are many north to south flowing rivers, Mississippi being the most famous, right? Are there any other rivers that are near Mississippi or similar to Mississippi, like north to south? Come again?
Missouri River.
The Missouri River is west of Mississippi, right?
Yes.
So let's say it flows something like this. Okay. Laminar flow, if you think of those streamlines like the river, streamlines, stream meaning you stream along that line. If you start at a streamline, you end up at the end of that streamline, always for every particle in that flow, that would make it a laminar flow. Does that ring a bell, or that you're able to connect with that definition? So so definition, laminar flow is flow along layers or streamlines that do not mix. So if I have a pipe, and let's say I have a laminar flow going on here, and if I have a way to inject a dye, okay, if I inject this dye along a certain streamline, and let's say that dye is nothing but like a drop of ink in the flow, that dye would only be carried by the flow along the streamline and would not be found here, or anywhere else. It is going to be only found at the end of that line. In some sense, the movement of rail cars or trains is a perfect analogy, because if you get on the train, unless the train derails, the train is going to go and end up in a particular station or destination. It's not going to end up randomly in your house. It's going to be only if you get in station A, only to station B. That is kind of an analogy for laminar flow. That makes sense? Yeah.
Laminar flow doesn't mix at all, or it doesn't mix significantly?
Doesn't mix significantly because the flow itself is carrying the dye or the visualization aid. The visualization aid is nothing but some chemical molecule, like it could be ink or dye or something. It is still diffusing. There is at a molecular scale, that dye is still kind of going around. It will slowly diffuse around. So as the dye goes further and further downstream, you can see the dye's width broadening, but the fluid is not mixing it. That is diffusion or thermal mixing. Okay, so if you watch this for a long time, what will happen is the dye's profile will slowly broaden. But if you had turbulent mixing, that is the other end of this, these layers, if the flow is so violent and the random fluctuations are so strong, what will happen is this thing will mix and you will have the dye almost entirely in the cross section. So you just drop a drop of ink, instead of it being carried like a little line, it will just become, the entire thing will become blue or red, whatever the color is. Okay, that would be turbulent flow. In fact, you defined laminar as absence of fluctuations, right? We can also define turbulent flow as the absence of uniformity or the presence of interstream mixing. If you want to identify a turbulent flow, the surest way to do is drop something in there and see it mix almost instantly for the entire flow. That would be turbulent because the irregular fluctuations will basically slosh around the dye and spread it everywhere. Okay. Okay. So we have a qualitative sense of what is laminar and what is turbulent. And trust me, this picture that I've kind of told you will only keep getting better or different in your mind as you think more about this, because you can this is not the only laminar flow possible, meaning this is pipe flow. But if you think of flow around a sphere or flow around some object or different flow situations, you will see how laminar flow can be also very complicated and it can also have some nuances. Okay, we'll leave it there. The question comes down to, for a given pipe flow, how do you decide whether a given flow has to be laminar or not? That is the important question when you are calculating entrance length. Okay, you got a Reynolds number of 26. Is 26 laminar or turbulent? That's the question. Towards the end of last lecture, we kind of made a analysis or thinking where we said Reynolds ratio is the Reynolds number is the ratio of two energies. Do you remember that? What is it? Reynolds number is the ratio of
Energy with frictional energy.
fluid kinetic energy, which scales as rho d cube v squared, to energy dissipated by viscous effects, which is anybody recall from their notes?
UVP squared.
Mu v d squared. Or was there another d? Yeah, mu v d squared. Mu v d squared. Okay. So fluid kinetic energy over energy dissipated by viscous effects. And we said that when you say Reynolds number is, let's say, 100, the literal interpretation of this is there is 100 times more fluid kinetic energy in this flow than what friction can dissipate at any given time. Okay. But just because there is more, okay, I think I should say it the other way. What is the consequence of having a lot of kinetic energy? Think about it. Then let's say you have Reynolds number 100, or let's say you have even a higher Reynolds number 10 power 5, or you have a Reynolds number of only 1. What is the consequence of having a lot of kinetic energy in the flow?
It's harder to control
Why is it harder to control?
because if there's a lot of kinetic energy. It should, I was just thinking it's harder to stop.
Your answer is correct. Your answer is correct. You intuitively said it. I just want to put words to your instinct.
If the pipe was to be like cut, there'd be a lot of fluid coming out, like a lot of momentum, so.
There's a lot of momentum in there,
Exactly.
okay? So why would lot of momentum or what would lot of momentum lead to? If you have a flow which has a lot of momentum, what is going to happen? What happens to any tiny fluctuations in the flow?
To get higher,
Louder, please.
higher collisions,
Collisions between what?
the various fluid particles.
So if you have a lot of kinetic energy, you can think those fluid particles are kind of moving fast, okay? What happens when you have, let's say, all of us running really fast or stampeding to exit the room in this at the same time? What happens if let's say we are all orderly and we all wait for each other and then everybody one at a time we leave, as opposed to all of us rushing for the exit at the same time? What happens later? Any disturbance, let's say we are all running towards the exit, and let's say I trip and I fall on my neighbor, that disturbance will quickly propagate through the crowd because we are all kind of running towards, everybody is moving fast. Any disturbance will kind of propagate faster before the fluid can readjust or before we all can readjust our positions. Do you see that? That is, any tiny disturbance will grow quicker when there is more velocity or kinetic energy going around than when there is less kinetic energy. Because if you had less kinetic energy, and let's say you make a disturbance here, that disturbance will propagate slowly, and your wherever the neighbor or the neighboring fluid particle has time to readjust its position and maybe get out of the way so that the disturbance can propagate. The important consequence of high Reynolds number is essentially to say any disturbance will grow quicker. Okay. What happens the other way? That is, okay, Reynolds number high. Reynolds number high means any disturbance or disturbances grow or multiply at a faster rate. What happens when Reynolds number is low, like 1, when kinetic energy and viscous dissipation are almost on parity?
Energy taken by the viscous interaction is able to eat up all the disturbances there.
The disturbances quickly get damped out because any increase in velocity will quickly be consumed or kind of sucked in by the viscous dissipation. Viscous dissipation is basically like a sponge which can soak up excess momentum in your flow. If there is excess momentum, viscous dissipation will kind of ramp up its work and essentially take it out of your system. It's kind of like the Federal Reserve. If there is too much money in the system, they increase interest rates and suck the liquidity. Those who are into the financial mind. Anyway. So at low Reynolds number, disturbances are effectively damped out by viscous forces, viscous or dissipative forces. So a high Reynolds number is almost universally correlated with disturbances multiplying faster, and a low Reynolds number is almost universally correlated with viscosity winning over inertia. Okay. So when disturbances multiply faster, how does it manifest to your eyes? When you see a flow in which Reynolds number is high, and let's say you take a very small object and you drop it in the flow where the flow has a lot of kinetic energy, you create a disturbance. What will happen to the rest of the flow? You can think that any disturbance that you introduce in the velocity will only quickly multiply and kind of go over the entire flow. Meaning, let's say you have a flow going on here, and the Reynolds number is quite high, let's say around 100,000, even if the flow were disturbance free in the beginning, all it takes is one or two disturbances at the mouth, and that disturbance will quickly propagate downstream and make the entire flow non-laminar or turbulent. Okay, so this high Reynolds number leads to turbulence unless extra care or sometimes extra care is taken to weed out disturbances. Okay, if you have a flow with very high Reynolds number, even if it were kind of steady or looks laminar for that moment, all it takes is a few disturbances to kind of make the whole thing become turbulent or transition to becoming turbulent. There's a very famous example of this. Okay, actually, I'll wait 2 minutes later. What happens on the other end? When your Reynolds number is low, when viscous dissipation is quite effective in sucking out any excess disturbances through dissipation, what can you do? That is, even if there are disturbances, the viscosity will take care of it. Okay, in this case, this leads to turbulent, this leads to laminar flow unconditionally, meaning even if there are disturbances, unconditionally, meaning even if there are disturbances, the viscosity will just suck everything out and maintain it as laminar flow. Okay. We know these numbers, okay? So we'll kind of erase this. So based on Reynolds number, a high Reynolds number is it amplifies any present or introduced disturbances which quickly transitions to turbulence, which is nothing but cross stream mixing. Transition to turbulence unless extra effort is taken to keep the flow disturbance free. Any velocity fluctuation that you introduce can transition to turbulence. So you have to use extra care to make sure there are no velocity fluctuations to preserve laminarity in a high Reynolds number flow. On the other hand, when you have low Reynolds number, any disturbances are so effectively damped that the flow almost universally is laminar, meaning no cross stream mixing and the flow is unconditionally laminar. Meaning even if you try, you can't make it turbulent. This is the dichotomy for any flow. Flow over a baseball, flow over an aerosol particle, flow in a pipe, flow in an artery, whatever the flow is. Reynolds number basically tells you whether you are in a flow with a lot of excess inertia or you are in a flow that is dominated by viscous precipitation. Okay. Whether or not, okay. So for any flow, I'll write this because it's important. For any flow, there exists, or I should say, there seems to exist, because this is the experimental finding, not a theoretical finding. There seems to exist a critical Reynolds number below which the flow is unconditionally laminar. That is, if the Reynolds number of your situation is below the critical Reynolds number, you can write this flow will be laminar. At least we haven't found contrary examples or conditions. Okay, if it's below that critical number, it is laminar. You can say that. If Reynolds number is greater than the critical Reynolds number, the flow can exist as laminar flow if extra care is taken to prevent any velocity disturbances from appearing. It can exist as laminar flow, but if left unattended, will almost always transition to turbulence. So the lower limit is a sure thing. You are below the critical Reynolds number, it is laminar. You can say that and go. But it is, if it is above the critical Reynolds number, it could be laminar if you take care, or if you don't take care, it will likely transition to becoming turbulent flow. Only question is, what is this critical number? What is this critical number? This critical Reynolds number is not a single universal number. It varies with flow geometry. Sorry, what was that? Somebody said something.
I said it's based on the problem.
It varies with geometry. Geometry is a broader word. So if you are thinking about, let's say, pipe flow, which is an internal flow, you can think of another situation like a flow over a sphere, and you could think what is the critical Reynolds number for this flow, or flow over an aeroplane or a car, or any flow will have a critical Reynolds number, which you can only determine through empirical methods like experimentation. You set the Reynolds number at, let's say you set it at 1. It seems to be laminar. At 10, it seems to be laminar. At 100, it seems to be laminar. At 500, it seems to be laminar. At 1000, it seems to be laminar. At let's say 2000, it still seems to be laminar. But let's say I do 3000, it starts to become oscillatory or turbulent. I have to literally do the experiment you have to do the experiment to figure out where the transition Reynolds number is. But luckily, 200 years of experimental work in fluid mechanics tells us where that is for at least pipe flow. For pipe flow, this critical Reynolds number is 2300. That's the magic number that you have to remember for your exams because we are dealing with internal flows. Below 2300 for a pipe flow, it's laminar. Above 2300, it's complicated. Could be laminar, it could be turbulent. Where they get this number 2300? Empirical evidence. People have measured it, people have done it multiple times in multiple locations and by multiple people. So we all believe that 2300 is correct. So question, if the Reynolds number of your flow is 26, what can we say?
Laminar.
26 implies laminar. So in our problem, we estimated the Reynolds number to be 26. So we have to pick the laminar formula and then say entrance length is 0.06 times the Reynolds number, which is 26, times the diameter 8 inches or 0.4 meters. So that gets me how much?
0.625.
0.625 meters. Okay, so that is the discussion on entrance length. You don't know the full length of the pipe. The problem didn't say that. Okay, but for the given conditions, Reynolds number was 26. We have to pick the laminar formula and compute entrance length based on that.
Wait, so is the L given on this problem?
L is not given. Approximately how long is the entrance length in this pipe? That's all asked, and that's the answer. The problem is basically an excuse to go into what is laminar, what is turbulent, what is entrance length, and how to use Reynolds number as a marker for that transition from laminar to turbulent. And if you get a certain Reynolds number, how do you make a judgment call? Suppose if the Reynolds number in this problem, I can set it up to get a Reynolds number of 10,000. So when you see a Reynolds number of 10,000 for a pipe flow, what is your immediate instinct? What is most likely outcome? Turbulent. But if I say that I took extra care to kind of machine the pipe so smooth that any roughness on the pipe walls have been kind of smoothed out, that the wall doesn't introduce any disturbance, and I took a lot of care to introduce the flow in a very, very uniform and gentle manner so that there is no incoming disturbance. If I took all that care, there is still a chance that we could maintain laminar pipe flow at 10,000. That is the extra care I'm talking about, machining the pipe, smoothing it, making sure the inlet flow is disturbance free and so on. Yes.
So on an exam, would there be an instance where you give a high Reynolds number, but you put in the exam so-and-so took extra care of it so that we assume that it's laminar flow?
So in some sense, the exam is a very poor sample of reality, in the sense I have to tell you, consider it to be laminar. Because I can't tell you a story of, I can say I did machining of the pipe, we did make sure nothing, no disturbance in the inlet. None of that actually guarantees the outcome. You could be running a wind tunnel. You might spend a lot of time sanding your pipe walls, or you could put a mesh upstream and make sure the inlet flow has no disturbance and everything is, perfect. That doesn't guarantee the outcome. The only way I can tell you in an exam is assume laminar flow. That makes sense?
Assume laminar flow is low and
For low, I won't say anything. I don't have to say anything. If it turns out to be lower than 2300, I don't have to say anything more. But if it is above 2300, if I don't say anything, the most safest assumption you can make is it's turbulent. If I want you to think otherwise, I have to say it. That's the only.
But that's what I meant, like, in an exam, would there be an instance where the person, oh, never,
I answered your question. I have to say whether you have to assume laminar or turbulent. I will choose to say nothing if it's going to be below 23. Yes,
So basically, we can, for at least an exam, we can assume that if the Reynolds number is above the critical number, it's, and if it's below, it's laminar.
if nothing else is said in the problem.
Okay.
Okay. All right, good. Let's get one more example. Okay. So I wanted to do this estimation. When you go to a gas station and pump gas, let's say you fill your tank 15 gallons, okay, some decent car. And have you kind of do you have a sense of how long it takes to fill 15 gallons, a tank of 15 gallons? How long are you standing there looking around and
3 minutes.
2 or 3 minutes.
3 minutes? So it's like 15 gallons over 3 minutes. So that's kind of your flow rate, right? Okay. And for the pipe or the tube that is carrying the gasoline from the pump to the car, have you noticed how much is the diameter roughly? Maybe an inch,
Like 4,
1 inch,
like 2 inches maybe.
1 to 2. We'll call it like 1.5 inches. And you know it's gasoline. They even tell you the octane number. You can look up its properties very precisely. So for gasoline, you can look up density and viscosity. In fact, density is if you paid attention to the pump where you make the payment and everything, there will be a sticker. Has anybody noticed Tennessee Department of Commerce sticker that says the gasoline from this pump is certified to have a certain specific gravity? That's a marker of quality, because if they adulterate your gasoline and sell you gasoline that is mixed with something else so that the density goes down, or basically less gasoline than what you pay for, that's a crime, because the state regulates the quality of the gasoline sold here. You can look up the density of gasoline, you can look up its viscosity, and you can estimate Reynolds number based on this information. Okay, the job of the engineer is not to know deep theory right away. Theory is needed, but to start with what is observable. So you pump gas, you know the flow rate, you know the diameter, you know what the fluid is. You should be able to tell what the viscosity is. And for that, sorry, not viscosity. You should be tell what the Reynolds number is. For that Reynolds number, is that flow laminar or turbulent? You should be able to tell. Because it's a pipe, you should be able to tell. But you have seen the flow. When you've seen it gush into your tank. Is the flow laminar or turbulent?
Laminar.
Are you sure?
And it reaches like a steady state.
I'm not talking about engine oil, I'm talking about gasoline. Like when you pour engine oil, it will be laminar. You can check this. You can, next time you go to the shop, you can actually pour the engine oil and see that it's a very thick fluid, that it will be laminar. Because the viscosity is so high, this number is low, which makes it laminar. But gasoline, you have seen, if you see it, it will be turbulent, unless I'm mistaken. Right? It'll gush out. It's not anything regular. That's an example of a turbulent flow. So after this class, after learning about what is Reynolds number, and it depends on these very simple observables, you should think about what's the Reynolds number for some commonly encountered flows. So you open the tap at your home, water comes out. You can adjust the faucet and you can make it come very slow drip, or you can increase the velocity and then full. So I don't know if you will do it. It'd be fun to try, but your faucet, usually whatever the type of faucet is, it has a position. Let's say this is the 0 position and this is the maximum position. And the flow rate will vary with the position where you set it, right? Typically every faucet works with it. So you can try to calculate what's the velocity or flow rate as a function of the faucet position. Or you can convert the flow rate into a Reynolds number, okay? And you can estimate what's the Reynolds number of the water flow when it exits that pipe. That is one observable. That is, you can try to calculate what will be the Reynolds number of the flow as it exits the pipe. Okay. There is one more observable there that you can do. What else do you observe? The outcome, right? You know the outcome. You look at the flow, you can tell whether it's laminar or turbulent, depending on how steady and uniform that flow is, right? So you can also say at every instance that you observe, you can say whether the flow is laminar or turbulent. So here is an exercise that you can do to test this 2300 business, which is the critical Reynolds number. You adjust the position. You start at 0 flow, meaning when the faucet is closed, there is no flow. Obviously, Reynolds number is 0. And then as you open it, the Reynolds number should increase, and this is the maximum. Okay. Try to figure out when the transition from laminar to turbulence happens, what is approximately the Reynolds number? It's not an experiment that requires you to build the Large Hadron Collider. You just need to use the faucet in your home and estimate the dimension of the pipe, look up water viscosity. How do you measure flow rate?
You can get a cup and then just put a timer.
Cup and a timer, known volume, measure time, you get the flow rate. The measurement you can do and verify whether I am piercing about 23. You can see whether 2300 really describes this transition from laminar to turbulence, right? So you could try this if you want, okay? But what I'm trying to say is, to develop good intuition in fluid mechanics, more than learning the math first, you should develop intuition to do measurements and observations first. Because the number of observations you could make are infinite. But if you don't know to observe or you don't pay attention, it becomes very hard to connect with TA. Okay. Anyway, that was some unsolicited opinion. Okay, so I have exactly 7 minutes. I'm going to do a derivation in 7 minutes. Can I erase this time? Okay. So we have now come to a point where we have estimated Reynolds number. Based on Reynolds number, we have done a discussion on what is laminar or whether the flow is laminar or turbulent. We have estimated the entrance length. In many cases, we may establish that it's only a small fraction of the total length. And then, for fully developed pipe flow, we need a relation between flow rate and pressure drop. Flow rate and pressure drop. Okay. So here is our situation. we have our pipe. The flow coming in is already fully developed, so we have some fully viscous profile which we don't know yet. We'll derive it. Okay. And we have the length of the pipe. Let's say we consider a section whose length is L and diameter is D. Okay. And we have the fluid's density and viscosity being rho and mu. And the flow rate through the pipe would obviously be Q. And from control volume analysis, can we write an expression for Q in terms of the velocity profile? I mean, you know this. What you don't know is the velocity profile. But if the velocity profile is given to you as VR of R, can you write an expression for flow rate as an integral? You did this for your exam too. Does it ring a bell? Flow rate in terms of the velocity profile. What we don't know is, we don't know VR of R yet. If we knew that, we'll be able to calculate flow rate. Okay. So what the message is, flow rate is a function of this velocity profile and diameter, or instead of R, I'll say D over 2. Okay. And flow rate can be calculated using or calculated if the velocity profile is determined. Okay, and when the flow traverses a length L at a flow rate Q, there is a drop in pressure. That's what we call pressure drop, delta P. Why? We talked about this at the beginning. Why would there be a pressure drop when you travel a certain distance? Friction converts fluid kinetic energy into thermal energy and essentially siphons it out of the system. Right? The wall is essentially a way for converting fluid kinetic energy into heat, and the heat would escape out eventually, leaving the fluid slower or with lesser kinetic energy. So we want a relationship between Q and the pressure drop. 2 minutes. If the flow rate were higher, would the pressure drop be higher, or in other words, will the pressure drop increase with increase in flow? Do you think, or the other way? For a high speed flow, okay, let's have a high speed flow versus low speed flow. In which case is the pressure drop higher? In which case is the friction higher?
High speed.
High speed. Friction is higher in high speed flow because the shear stress scales as viscosity times the velocity gradient. If the velocity were higher to begin with, the velocity gradient would also be higher. You can think the velocity gradient is V over the radius. If V is higher, shear stress is higher. If shear stress is higher, pressure drop will be higher, right? We also know the pressure drop depends on, or pressure drop over rho V squared depends on L over D and Reynolds number. We did the scaling analysis on Tuesday. We did this, okay? Now, in the 1 minute that I am having, to get this relation, I'm going to tell you Q is pi over 128 mu delta P over L times d to the fourth. I am telling you this equation. It has a name. I'll tell you the name in the next lecture. But to get the derivation, I want you to watch the video. Because in the video, I spent a lot of time doing the derivation and I don't want to go through it entirely. It's done pretty carefully, I think. And if you watch it, you should be able to see the steps of how we get this. So please do me a favor. By Monday, you are expected to watch all the videos and upload a statement saying you have watched them to get 5 points. So please do that diligently. Do really watch the videos. Don't just say it. And if you had watched it, you would have seen this derivation by the time we meet again on Tuesday. Okay. So please do that and we'll meet again. Thank you.